Stack too deep? Every Solidity dev has hit it. What if there was a simple fix? One flag in foundry.toml, no contract rewrite, and the error is gone. I saw this via IR speedrun by Nikola Matić from the Solidity team, and I think the practitioner story got buried under the flowchart. So here's what via IR actually does, what it fixes in your code tomorrow, why the fix works, and the one place where it still costs you. Here is what triggers it in real code. A function with maybe 12 local variables, call data, a few intermediate hashes, a couple of struct fields you destructured for readability. The Solidity compiler refuses to compile it and tells you the stack is too deep. The accessible part of the EVM stack is only 16 slots, and the legacy compiler cannot move variables off the stack once you run out. So you do what every good modern developer does. You fire up Claude, ask it to fix the error, and pray. Honestly, that might work, but the better idea is to fix it by hand. What every working Solidity dev actually does is wrap part of the function in an extra block to force a variable out of scope earlier. Or split one function into two, so the second function gets its own fresh stack frame. Or pack 3 parameters into a struct so they count as 1 slot instead of 3. Here is what I did. I opened the same contract in VS Code. I scrolled down to the Foundry config file and I flipped one line. Via IR equals true. I saved the file and I ran forge build. The compiler chewed on it for a noticeably longer second than usual. That part is real. The compile time does go up, but then it finished clean. The contract that was about to need a scope block just compiled. That is the entire user-facing change. It is honestly anticlimactic. But think about what this means for the next 6 months of your code base. Every place where you would have reached for one of those workarounds, you do not have to anymore. The function reads the way you wrote it the first time, before the compiler forced you to contort it. Now let me walk through the second flavor. The first one is the obvious win. The second one is the interesting one. I opened a different function. This one already had a scope block from months ago, back when I had paid the workaround tax. I deleted that scope block, then I rebuilt with via IR on. The function compiled fine, the test still passed. The gas snapshot moved by a single-digit number of units in my favor. So that scope block I added back in November, it was not protecting me from anything. It was working around a compiler limitation that has now been lifted. The workaround code was load-bearing for the compiler, but it was never load-bearing for the contract. That is the part that is easy to miss when you read the release notes. The fix is not just for future contracts you have not written yet. It is also a cleanup pass you can do on contracts you already shipped. Here is the part that confused me when I first heard it. Someone in the Quanda asked Daniel from the Solidity team why some legacy contracts fail to compile under via IR. And his answer was the opposite of what you would expect. He said via IR uses more intermediate variables, not fewer, and that is exactly why it produces fewer stack errors. The reason that sounds wrong is that more variables should mean more stack pressure. But the legacy compiler had no choice. Every variable had to live on the stack, and the stack has 16 accessible slots, full stop. With Yule as an intermediate step, the compiler can spill. It can park a variable in memory instead and load it back when it is needed. So the count of variables stops mattering. What matters is how many of them have to be live in stack slots at the same time. And the answer with via IR is fewer than you thought, because the compiler will move the rest. So here is the actual pipeline, end to end, because once you see all 5 stages laid out, the spilling story makes more sense. Stage 1 is your Solidity source, the code you write, the file the compiler reads. Under the legacy pipeline, the compiler turned that source directly into EVM assembly, which is the human-readable form of the bytecode the chain executes. The legacy optimizer then walked over that assembly looking for known patterns it could rewrite into cheaper ones. And once it ran out of rewrites, you got your bytecode. 3 stages, 1 optimizer, 1 pass. The via IR pipeline keeps the assembly stage and the assembly optimizer at the end, but it inserts 2 new stages in front. Stage 2 is Yule, an intermediate representation Solidity has had for years, originally as the language inside inline assembly blocks. Yule looks like a small, untyped, low-level language with named variables and function calls, and it is significantly easier to read than EVM assembly because it has not been flattened into a stack machine yet. The compiler translates your Solidity into Yule first, which is the IR step the talk is really about. Stage 3 is the Yule optimizer, a second optimizer that runs over the Yule before any of it gets turned into assembly. And this is where the stack too deep relief actually comes from. Because Yule still has named variables and structured control flow, the optimizer can make a real decision about which variables to leave on the stack and which to spill into memory. The legacy pipeline could not do that. By the time it saw your code, it had already been flattened into assembly, where the only addressing mode for a local variable is push it onto the stack. Stage 4 is the EVM assembly step, the same one the legacy pipeline uses. The Yule gets lowered into stack machine instructions. Stage 5 is the assembly optimizer, the original one, still running because it catches patterns the Yule optimizer cannot see, and then you get bytecode. So when Daniel said the new pipeline uses more variables but produces fewer errors, what he meant is that the Yule stage gives the optimizer enough context to make spilling decisions before the code becomes a stack machine. More variables enter the Yule optimizer, the optimizer parks the ones that do not need to be hot in memory, and the assembly that comes out has fewer simultaneously live stack slots than the legacy pipeline would have produced for the same source. The escape hatch is not cleverness in the optimizer. It is the fact that there is now a stage where the optimizer can see your variables before they have been flattened. That is the whole story. Now the honest part, via IR is not free. Compile time is the one that hurts day to day. The Solidity team's own framing is that this is roughly 2 to 3 times slower than the legacy pipeline, because you are running 2 optimizers instead of 1. On a small contract, that is a second you do not notice. On a Foundry test suite that recompiles 50 contracts every time you change one line, it adds up. Gas costs are almost always slightly better under via IR, but there is a small set of edge cases where legacy still wins by a few units, and full stack too deep elimination is not here yet either. That waits on EOF, the EVM upgrade that lets functions have their own stack frames. For now, via IR reduces the pain. It does not retire it. So the short version of all of this, turn via IR on for most projects. The pipeline has been stable since 2022, the gas numbers are usually a win, and the workaround code you wrote last year just got obsolete. The original speedrun from Nikola Matić is the place to go if you want the compiler team perspective on what is still pending. Next time, I want to dig into the EOF upgrade, because that is the one that finishes the job. If this helped, subscribe for more. Code samples and the full walkthrough are on the blog. Link in the description below.